Greetings, my name is Dennis Helsel, and today we're going to talk about data analysis methods for data with non-detects, and particularly about the cost of complacency of using very common methods that are totally inadequate for the job. These common methods for non-detects have a very high cost because they make errors, sometimes bad errors. And so here's three of those common methods. They might be the three most common offenders. The first one is substitution of a half or some other fraction of the detection limit or quantitation limit or reporting limit, depending on what the laboratory gives to you. So putting in something between 0 and 1, usually 0.5, 0.7 are common fractions used, times that limit for all data that are non-detects. I'll be spending most of the time today on substitution because it's most commonly used of these three methods. The second method that's inadequate for handling data with non-detects is the deletion of those non-detects prior to doing your data analysis. So you might throw out something like the lowest 30% of your data and then try to make some sense out of the upper 70%. And as you can imagine, that might not work very well. Thirdly, people interpret percent detections but don't pay attention to the fact that those detection limits are changing. So those are the three methods I'll talk about, though most of the time I'll be talking about substitution today. Why do we care about these methods when we have non-detects? Because non-detects occur in some of the most important chemical parameters that we measure. Most contaminants that we measure in water, soils, biota have non-detects, because we're interested in things that often occur in trace levels, but those trace levels can be toxic. So, trace metals, certainly for years and years, have had non-detects. Older hazardous substances like PAHs, newer hazardous substances, neonicotinoid insecticides, or pharmaceuticals, all of these commonly have a substantial portion of their data that are non-detects. And inorganics that are of ecological concern, such as nitrate, is still one of the things that we worry about for eutrophication purposes. If you don't remember anything else, there's more information on what we're going to talk about today and what we're going to talk about in May on methods for data with non-detects in a book that I wrote called Statistics for Censored Environmental Data using Minitab and R. It's the second edition. It came out in 2012, and the first edition came out about 2004 or 5 under a different title. The only thing I want you to know about this book is that it does have more information, and also that the title, the word censored, is a statistical term that means known only to be greater than or less than a threshold. So it means we don't have a single number for an observation. We only know that it's less than 1, or greater than 10. That's censored data. And there are methods in statistics for censored data that have been around for decades, some going back to the 1950s. And environmental sciences have not used them until recently, and I hope that my books have had some impetus for having people change and use them. And that's what I'm trying to do today with you, is to convince you and the people that you work with and the people that write regulations that you're working with to change what they call for doing data analysis methods when non-detects are present. So what's wrong with substitution? First, it strongly affects the variation of data. Think of it as the standard deviation. Often decreases that because you're putting in a series of numbers that are all similar to one another, but it may actually increase the standard deviation as well. Second, it adds an invasive pattern to the data that is alien to the data you've collected. And substitution is not neutral. It's much worse than, somewhere between I know the number's somewhere between 0 and 1, so I'll put in 1/2. Third, it produces poor estimates and incorrect statistical tests. You can get the wrong answer. You can find a trend that's not there in the field just by substitution. It produces a change in the shape of the data distribution. So the shape of the data, why do we care about that? That shape is used for a variety of decisions in statistics and in applications, such as risk analysis. And there are far better methods, finally, that are available. They're available right now. They've been available for decades. You don't need a PhD to do them, and you can find them in software. All you need to do is be familiar with them and familiar with the reasons why you want to use them and you don't want to use the commonly used methods. So first, the substitution of 1/2 or something like that changes the standard deviation. And the issue here is that we're not just substituting one number, we're substituting a whole series of numbers. So let's say there was one detection limit. Then we're putting the same number over and over into the data set. What do you think that does to a measure of variability? Usually it decreases it. So here's an example. This is a box plot, a plot of percentiles. The standard deviation for this data is 1.02. Now I'm going to declare that there's a detection limit at 2 in the laboratory. So everything below that 2, about maybe 60% of the data, is now less than 2 when it's reported to you. So what do? You say, less than 2s, I'm going to call all of those 1s. So everything below the 2 actually isn't there. And you jump from this box, draws lines down, but really the data are sitting up here at 2, and then you jump to a whole series of 1s down here. That's a very unrealistic set of values for this data, that there's no decrease below 2 that's nice and smooth, and we know it's not true. And it changes the standard deviation down to about 0.84. So we have decreased the standard deviation. Why is that of concern? Well, first, it affects things like confidence intervals. Confidence intervals, the width of those intervals depends on the standard deviation. So when you stick in a lot of the same numbers and lower the standard deviation, you get confidence intervals that are too short. In a very large simulation study, Singh and others in 2006 found that when you put in 1/2 the detection limit, it does not provide adequate coverage. That's statistical jargon for the ends of the confidence intervals are not high and low enough. The UCL 95, the upper 95% confidence limit on the mean, is not high enough after substitution, that are as low as 10% non-detects. So those lower standard deviations produce lower confidence limits and intervals that are too short. They summarize their results with do not substitute 1/2 the detection limit to compute an upper confidence limit on the mean. This is true for confidence limits, that substitution affects it because of the effect on the standard deviation. Other procedures also depend on the standard deviation, including t-tests, analysis of variance, regression, and other methods, generally the methods that are in a class called parametric statistical methods, all depend on the standard deviation. So when you substitute for the non-detects, you change the results of those methods, and you're not changing them in a good direction. How long have people known this? Well, even longer than 1986, but back in 1986, another person and I published in Water Resources Research a simulation study that showed that substitution really did not perform well compared to other methods when you estimate means, medians, standard deviations, and other percentiles. Since that time, there's probably been at least 100 papers evaluating the effect on the mean. But the mean is the best case scenario for substitution. The mean is really not the issue. The issue is the variation. So in 1986, we found that the other methods were predominantly better than substitution, and often better by a large margin. That 1/2 the detection limit gave reasonable estimates for the mean when there was one detection limit. And if you find statements that the substitution is not too bad, it's usually because they only looked at one detection limit. but not for other statistics other than the mean, and not for data with multiple detection limits. For example, the bias of substituting 1/2 the detection limit for estimating the median was 4.5 times that than for a better method. And if I were in the news media, I would say it was about 450% higher. The bias was 450% higher than the better method. So there are other methods out there that do quite a bit better, and we'll talk about those in May. The methods that rely on the standard deviation will be off the mark after you substitute a fraction of the detection limits. And what I mean by that is anything including 0 or including 1 times the detection limit, so including the detection limit itself. All of those will destroy the standard deviation and the methods that depend on it. Second, substitution adds invasive patterns. Characteristics other than pollution concentrations often affect detection limits. So if we substitute 1/2 the detection limit, and that limit depends on the pattern of this other characteristic that's not the concentrations themselves, we've just put in a new pattern, an invasive pattern, one that has nothing to do with the concentration data out in the field. So here's 2 examples. Let's suppose we are interested in the diet of caribou or some other fauna, and leaves were part of that, and so they measured the arsenic concentrations in leaves. That's done usually by ashing those leaves to remove all of the water, and then measuring the concentrations in the ash, which is called in the ash weight, and then doing a multiplication times the percent of the sample that was ash, so getting rid of, in essence, the water portion, and saying that the ash weight times that percentage is equal to the dry weight of arsenic. Well, the detection limit in the ash may be 0.5, but the leaf materials have different amounts of water in them, and so this proportion, this percentage, differs between the samples. So when you multiply this together and the ash weight concentration is less than 0.05, you've just produced many, many different detection limits. And if you put in 1/2 the detection limit of all of those, you've just put in a pattern of the water composition in the leaves to the arsenic concentrations, and that's totally unrelated to the concentrations of arsenic that are actually in the leaf. Second example, this is the most common example that I've seen. Concentrations in something like a river over a period of time, let's say 20 years, and we measure those concentrations, but detection limits decrease over time. So the other variable that's not related to concentration necessarily is time. If I put in 1/2 the detection limit, that just adds in a pattern that's a decreasing set of numbers, higher in the early period because the detection limits were higher, lower in the later period. And that pattern, that decreasing trend pattern that you've just put into the concentrations, is not there in the river. And you very well could produce a trend, a decreasing trend in your results that's not there just because of substituting numbers. So here was just an example of that. I generated some data so that I knew what the truth was. There's no trend in this data. This is just noise up and down. And I'm going to take some of the smallest values and call those a detection at a detection limit, and then take 1/2 the detection limit. So here's the detection limits. They're twice as high as these numbers because these are the 1/2 numbers, and because the detection limits went down every couple of years, the 1/2 detection limits go down every couple of years, just to illustrate that visually. And so this pattern might be strong enough to outweigh the no trend in what's left of the data, especially if there's a large percentage of non-detects. Then that trend, that decreasing trend, could dominate, and you'd come back with a significant trend that is not there in the original data. Invasive patterns are often added in regression and correlation as well. So here again, I've generated data to know that there is a significant trend up. There is a significant regression. If you fit a straight line to this, there is a significant correlation. That correlation coefficient initially is 0.81. Then I'll go ahead and use two detection limits at 3 and 1. All the less than 3's become 1.5. That's the upper flat line here with open circles. And because of some different conditions, they used a lower detection limit at times. May have been a different laboratory or some other cause. And so those less than 1's become 1/2. After substitution, these are flat lines that are invasive. We have just taken data that had an increasing slope and put in a zero slope for them. And that combination, which you caused by substituting, changes the correlation coefficient from 0.81 to 0.55 and probably not significant. So it waters down the signal. There are methods for dealing with these non-detects that do not water down the signal, that do not put in an artificial flat line or set of flat lines. So using substitution is watering down the data. It's like watering down good wine. And what you end up with is water sometimes. This has been known again for quite a number of years. Thompson and Nelson, in a paper in Environmental Science and Technology in 2003, found that for censored Y variables, the variables on the vertical axis, substituting a half the detection limit for non-detects produced biased parameter estimates. Slopes in particular are too close to zero because we've just stuck in a whole lot of zero slope values. I won't call them data, zero slope values. And then artificially, that lowers the standard error, which is just the standard deviation of the residuals around the regression line. And that is used in the test for determining whether the X variables, the explanatory variables, are significant or not. And it is too low in terms of the standard error, so it causes some variables that should not be in the regression to appear significant, and you include them as explanatory variables, the X variables, in the regression. So you can really mess things up with substitution. There are much better ways. One of the places where there are much better ways is in a package for R called the NADA2 package. It's for censored data, again, data that are above or below a threshold. It does not substitute numbers. It does some other thing which we'll talk about in the May workshop. And these methods are valid for both when there is one detection limit and perfectly valid. In fact, those methods were developed when there were multiple detection limits, multiple thresholds. So what can be done, this is just a teaser, a picture for what you might be able to do after you see in May what methods are available. A regression of total mercury, this is a cube root, I won't go into why, of total mercury in fish versus the weight of the fish. So kind of a substitute for the age of the fish. And you can see there's a strong correlation, and you can fit a nice regression line to it. This is a regression line that uses the detected values, which are all the black circles, and the non-detects, which are represented here by the red dashed lines. So they're not represented as a point because we don't know what point to put them at. They're somewhere between 0 and the detection limit itself. And the information in these non-detects are really important. They add quite a bit to determining where this regression lies and how strong the correlation is, because if you notice, all of these non-detects are at the very low weight for fish. There are no non-detects out here. That's a pretty strong piece of information. That kind of information, where they are located, is very important for determining the final result, and that is used in these better methods. Thirdly, substitution produces incorrect statistical tests. This is just an example from the Ontario, Canada Pollen Monitoring Network. And there are pesticide concentrations measured in pollen at beehives that are closely located near corn growing areas. And we're going to look at thiomethoxam, one of the neonicotinoids, and nearly 100% of corn seed and soybean seed, a large percentage, are treated with those before planting. And so we want to know is how much do those pesticides affect the plants as they emerge and bees as they alight onto the plants. The concern is for the honeybees, of course. Do the thiomethoxam concentrations differ in pollen located on the plant and picked up by the bees between two stages of plant growth, when the plant first emerges and then later on when the corn tassels appear? So we have these two. These are box plots again. The boxes are the middle 50% of the data. We can't see a lot of the data in the corn tassel, so the concentrations are lower, and they're clearly lower. And a good method should pick that up. We only see the data as far as detected values above the detection limit. Again, maybe closer to 70% of the data are down in this gray area somewhere. Unfortunately, what could be done, and often is done, is that all of those that are at 0.05, with just one detection limit, are put in as 0.025, one half the detection limit. And so we have this big jump down to the data here on the dashed line, not fairly representing the pattern of the concentrations all the way down. The result is a p-value of the t-test of 0.058. The criterion in statistics traditionally has been 0.05, which means this is not quite low enough to say that there's a difference between these two. So I want to remind you of what a p-value has been considered. It's the strength of evidence against there being a signal. So it's the strength of evidence against there being a trend, or against there being a group difference. So when this p-value is smaller and smaller, there's less evidence against the signal, and so more evidence that there is a signal, that there is a difference in this case between the two groups. And this is not quite small enough. This is just the t-test after sticking in a half the detection limit. And again, analysis of variance, which is another test that uses the standard deviation. These things are used to test for evidence of contamination, like a contaminated area potentially versus a control. Or they've used for the determination of levels that affect organisms, the no effect level. And this would still be considered no effect because it wasn't found by the t-test, perhaps. And because we substituted, that determination is totally wrong. So out of the NADA2 package for R is another method called, the command is called send one way. The test is called the PADO test, one of those tests that's been around, I think, since the 1970s for censored data. It can compare two groups just like this. Its p-value is 2 × 10 to the minus 13. So there's 13 zeros strung out before we hit the 2. That is 11 orders of magnitude lower than the p-value for the t-test after substitution. This is far better. It extracts much more evidence than the other test did, the t-test with substitution did, from the same data. The t-test is used in development of no effect levels and adverse effect levels. And not finding those effects due to substitution has likely caused those no effect levels to be too high. Lastly, the substitution changes the data distribution shape, and that's important for risk analysis as well. This is one measure of showing the distribution here. It's called a probability plot or a QQ plot. And there's a model for what the distribution might be, and that's this straight line that's fit down through the center. The detected values are plotted again as dots. The non-detects are not plotted because you don't have that unique concentration number to plot here. This is the logs, in this case, of atrazine concentrations. But this was one detection limit again, just to keep it simple for the plots. It works fine for multiple detection limits, but it's more detail than we have time today to talk about. So there were 30% of the data that were non-detects at the low end. So you see this first 30% going from 0 up to 30th percentile. That 30% of the data are blank here. But the fact that they are blank, it reserves that space for the non-detects, meaning that these detected values are plotted at their correct percentiles. So this dot here for the lowest detected value is just slightly above the 30th percentile. It would be at the 30 or 31 or 32nd percentile. So this is the correct way to plot probability plots. And you can find these in NADA 2, but you can also find these kind of things in some of the other tests that I'll talk about in May in survival analysis sections of standard statistical software. So that's the way it should be done. The way it's often done is to stick in a half the detection limit. You just put in a flat line here. That totally destroys the evaluation of whether this middle line, the model, is a good fit for the data. And it also alters the percentiles that these data are plotted at. And so you get the wrong percentiles for the data. You can fit the wrong distribution to the data. In general, it really messes things up quite a bit. So don't substitute in a flat line pattern when the data really are very unlikely to be all at the same number. They should be going down. So we want to do something better than this. This also applies to another way of plotting the distribution, and that's something called a cumulative distribution function, or CDF. This cumulative frequency here, think of it as percentiles. 0.5 would be the median. If I went over to this step function, the data are plotted as a step function. Fitted distributions, so a model, are plotted as these lines or curves. This kind of analysis is used in risk analysis for exposure distributions and stressor response curves and so on. The gray box shows the uncertainty with non-detect, so it's honest if it's done well. If you just stuck in a half the detection limit, there would have this, it would pick some direction depending on the concentration you pick. Somewhere around 1/2 the detection limit would be to the right of 0. And then the rest of these percentiles would be affected by that as well. So it is not a good, again, good result if you put in 1/2 the detection limit. All right, so that's the 4 things of substitution that are not good, plus a little bit occasionally there notice of what a better method might look like, which we'll talk about in a few months. So what else is wrong? Very quickly, the deletion of non-detects. If you delete the non-detects in the QQ plots, for example, what should be at the 31st or 32nd percentile, this smallest detect, is now plotted down around the 2nd percentile. So it totally destroys the percentiles of the data. And everything you do from this point on is going to be wrong. There's no value in trying to estimate what the distribution of the top 70% of the data are, because you have no control over what that percentage is. And it may be a different result if it were 50% non-detects and 50% detects. So and doing things like comparing groups also doesn't work after you throw out non-detects. There's a lot of information in the non-detects, specifically in the percent of the data set that are non-detects, and what that non-detect level is, what the detection limit is. So here's an example of a very poor analysis. This is plotting means with a bar graph. So this purple area is the mean for samples in this year, 1995, and then the mean for sources and the mean for systems. And the big picture here is that after 1996, the mean drops precipitously. Well, I believe there was a change in the laboratory detection limit between 1996 and 1997. They don't say it easily, but they're just looking at the detected data for MTBE. So they've deleted all the non-detects. So what happens when the detection limit decreases? When the detection limit decreases, there are smaller numbers, smaller concentrations that are now detects, quote unquote. So the definition of a detect changes. And those are now used to compute the mean in 1997 and after. And so we get, not surprisingly, lower concentrations for the mean. Similarly, just a different plot, if we were looking at things over time and we see the detection limit changes, the data that we use changes, and there's a lot lower values in the later years. And I have seen people argue that because the percent detects were higher, there's more contamination. Well, this is that data set I used for trend, where there really is no trend. It's just that when you go down lower with the detection limit, you've got more and lower data to compute a mean. It's also true that you've got more data to compute the percent detections. So there's no use in using the measure called percent detections when the definition of detection changes, when the detection limits go down or up or differ by different laboratories, etc., for any of the many causes that can change your eventual detection limit, dilutions in the lab and other things. If that's the case, you can't talk about percent detects. It's a lot better to talk about percent of your data above 0.3 or 0.2 or something like that. So comparing percent detects is only reasonable when the detection limit is constant. So what other methods are available? We'll see about that in May in the workshop. But all of these methods I will be talking about then do not substitute values like a half the detection limit for non-detects. They have much better ways of doing all these types of procedures. Thank you very much for viewing today.